Welcome back to the next video, everybody. Today we're going to be looking at more properties of the p-adic representations rho EP attached to elliptic curves E over Q. We'll break those properties into two categories. The first category will be when P is a prime of good reduction for E, and the second category will be when P is a prime of multiplicative reduction for E. And the reason we're doing this is because we're principally concerned with semi-stable elliptic curves over the rationals, and so every prime will be either of good or multiplicative reduction. So let's get into this. What's the setup? P is a prime, E over Q is an elliptic curve. The representation rho EP, this bar shouldn't be here, remember, encodes the Galois action on the inverse limit over n of the p to the n torsion of E. This inverse limit is isomorphic to zp squared, where zp is the p-adic integers. So here's the first property. Let's let E over Q be an elliptic curve with good reduction at a prime P, and let's let E tilde sub P denote the reduction of E mod P. If L is a prime that isn't P, let G sub L be a decomposition group at L. Let I sub L denote its inertia subgroup. The property is that rho EL is unramified at P, and the trace of rho EL of Frobenius at P is P plus 1 minus the number of FP points on E tilde sub P. So remember, when we're unramified at a prime, then locally at that prime, the image of Frobenius essentially determines the representation. So this is an excellent result. It tells us a lot about the image of that Frobenius. We get the trace, right? If we had trace and determinant, for example, then we could write down the characteristic polynomial and we'd be all set. Okay, so in particular, trace of rho EL of Frobenius at P is an integer, and it's independent of the prime L as long as L isn't P. So that's nice to know. Two, how about flatness? So again, we're in the case P is a prime of good reduction for E over Q. For all n at least one, there's a finite flat ZP group scheme F sub n, such that the p to the n torsion QP bar points are isomorphic to the QP bar points of F sub n as GP modules. So what this is saying is we don't really just have flatness mod P like we might expect if we read Theorem 1 from the last video, but we have flatness sort of all the way up at each level n for all the p to the n torsions of E. Okay, and the last good reduction property I want to look at is ordinariness. So if E has what we call good ordinary reduction at P, which means its reduction mod P has P torsion of order P, then rho EP restricted to inertia at P takes a very special form. It's got kind of two lines here, a cyclotomic line and a trivial line. So on the diagonal, we have chi sub P, the cyclotomic character, and we have 1, the kind of trivial character, I guess. Okay, another way of saying this, we have terminology for this. This is another way of saying that rho EP restricted to IP is ordinary. Okay, if instead E has good supersingular reduction at P, which means its reduction mod P has trivial P torsion, which is the only other option. You're either ordinary or supersingular. You can see the video on basic elliptic curve theory to see a little bit about why that's true. Then I can tell you what rho bar EP is restricted to all of GP. It's just irreducible. Okay. So proofs for all this stuff, I'll give you references. The first one follows from Theorem 1 and material found in Diamond and Sherman chapter 9. The second statement follows from Theorem 1, the elementary fact that the prime divisors of the minimal discriminant of E are exactly the primes of bad reduction for E, and proposition 8.2 in Edixhoven's book. Okay, so we talked a little bit about that book and that proposition last video. So this is a good little exercise for you there. Okay, statement 3 follows from Sayre's Galois properties paper, chapter 1. Although if you're going to read that, I think so. Sayre's IP is what we would now call the wild inertia group. So what we're considering is his I and I sub T, just in case you read it and you're wondering why the notation doesn't seem to match up with what I'm saying. Okay, how about multiplicative reduction? So I can kind of summarize the results we need on one page here. Suppose an elliptic curve E over Q has multiplicative reduction at a prime P. Let Q be kind of attached to E as per Tate uniformization, and let delta from GP mod IP to plus or minus 1 be the unique non-trivial unramified quadratic character of GP if E has non-split multiplicative reduction at P, and the trivial character otherwise. So if we have split multiplicative reduction at P. Then if L is any prime, two things are true. Rho EL restricted to GP has the same kind of form as from above. We have like an L-adic cyclotomic line on the diagonal and a trivial line on the diagonal, but then we have to tensor with delta. And if L isn't P, then the exponent of the so-called conductor of this representation at P, which I'll define soon. I'll be talking about the conductor of a representation in a separate video later. That exponent of the conductor is just 1 in this case, okay, which isn't surprising if you remember the definition of conductor of an elliptic curve. As long as that curve is semi-stable, it's just the product of all primes of bad reduction for that curve. But remember, I'm working in that case, with that definition, with a semi-stable elliptic curve. And so all the exponents of all the primes dividing that conductor are 1. Well, if the conductor of the elliptic curve has anything to do with the conductor of this representation, you expect that the exponent of the conductor at a prime of multiplicative reduction to be 1, right? And it is. That's what this is saying. Okay. 2, how about when we look at the mod L representation, rho bar ea, and if we restrict that to GP, we get the same kind of thing. We get chi bar sub L, the mod L cyclotomic character, and 1 on the diagonal, and then kind of this psi up here in the upper right, tensor delta. And what is this psi? And then also what does tensor delta mean? Psi is an element of H1 of GP acting on Z mod L Z1, the first Tate twist of Z mod L Z, okay? And you know from Galois cohomology, for example, from class field theory or wherever you might learn this, this is just isomorphic to QP star mod QP star to the L, so QP star mod L powers. But the thing is, like, Q lives here, so it has an image here. So you can think of Q as living here. And so basically psi lives here and corresponds to Q here. That's what, because these are maps and these are just elements. Okay, so I want a character here. All right, what does tensor delta mean? It just means multiply by plus or minus 1, depending on whether or not the image of the sigma you're considering under this representation has image plus or minus 1 under the character delta. Because remember, delta is just a character from GP mod IP to plus or minus 1. Okay, how about proofs? All of this basically follows from Tate uniformization, because Tate uniformization gives me that the QP bar points of E are isomorphic to QP star sub QP bar star sub P mod Q to the Z, kind of parentheses delta, as GP modules. And what does this parentheses delta mean? It means that GP is acting on the right-hand side here as sigma sends X to sigma of X to the delta of sigma. Okay, so you can see Silverman 2, chapter 5, for example. You can see Diamond-Taylor's Fermat's last theorem notes, which I'll call DDT from here on out, page 20 for more details. You can also see chapter 13 of my notes. And then finally, you can also see the last page of my separate notes, which I will send you if you want, on Sayre's open image theorem, and also my notes on Sayre's Galois properties paper, because these are kind of intimately related. To me, these are the open image theorem papers and books. Okay, so next time we will take all of the information we've learned about Galois representations so far, and we will begin applying that information to the theory of the Frey curve. And so I'll see you then, and thanks for watching.